My name is Anastasiya Bosova and welcome to the final presentation of my master thesis project, which was dedicated to the heuristics for the design of low-carbon districts in the tropics. So in the next 30 to 40 minutes, I will give you a brief introduction into the topic. Then I will address the most important findings of the literature review that helped to develop the methodology of the project. Next, I will talk about the methodology of the study. And finally, I will show the results. And of course, conclude and give an outlook. And afterwards, we'll have a discussion and everyone is welcome to ask some questions. So let's begin. I couldn't resist to start with this picture that was recently shared by Professor Schmidt. He argued that probably a small percentage of world's population will be affected by COVID that has gained enormous attention by global community. Certainly more people will be affected by the upcoming economic crisis, but all of us without exception will be affected by the negative impact of climate change that is caused by anthropogenic greenhouse gas emissions. And cities play a big role here. Cities are estimated to cause over 70% of global carbon emissions, and the building sector is responsible for more than a half of those. More than 50% of world's population already today lives in the cities, and this percentage is only expected to grow by more than 70% in 30 years, with a particular growth occurring in the cooling-dominated regions of Asia, such as Singapore. You can see Singapore in the city, in this picture. This is the city center, but actually I can't be sure that this is Singapore because it's third month of lockdown, but we can assume that. So yeah, there is a clear challenge of mitigating climate change and sustaining needs of growing population at the same time. And this is impossible without low carbon solutions in the building sector, which would aim to reduce its energy use. Despite this emerging need for planning low-carbon cities, urban practitioners are still experiencing a lack of low-carbon design guidelines. It has been argued by various researchers that it would be helpful for urban planners and architects to have a guidance at the neighborhood level, or I will later call it district scale, such as which design parameters can potentially influence energy performance of the urban area. However, the influence of the urban design parameters on the district energy performance is not sufficiently explored and quantified to come up with the comprehensive guidelines. So this thesis attempts to fill in this knowledge gap by quantifying the influence of the urban design parameters on the district energy systems in Singapore. More specifically, the influence on the operational carbon emissions of the district energy systems. And based on this, the final goal is to derive heuristics or shortcuts that would help the urban practitioners to design low-carbon districts in tropical climate. So the first step of the thesis was to conduct a literature review. It had two goals. First goal was to study existing low-carbon or low-energy urban design guidelines. And second goal was to review energy-driven urban design studies, which explored the interdependence between urban design parameters and energy performance. Regarding low-carbon urban design guidelines, there were only few sources found, mostly related to China or India. They would introduce general low-carbon strategies such as deployment of renewable energy, use of highly efficient appliances, and so on. So it was rather a vague conceptual level, and it didn't provide the clarification on how urban design parameters influence energy performance of an urban area. Moreover, urban form was only considered as a factor that influences CO2 emissions associated with transport sector. So there was a concept of transit-oriented development introduced that recommends to concentrate density around transit stations to reduce overall commute. So to conclude, the lack of low-carbon urban design guidelines could be confirmed in the first part of the literature review. The second part of the literature review studied the concepts of energy-driven urban design. Its main approach is to consider interdependencies between the energy systems and the urban form in order to achieve higher energy performance. A recent paper reviewed 50 energy-driven urban design studies and found the design parameters that show higher correlation with energy performance of the building than other parameters. These include typological parameters such as floor area ratio, orientation, and site coverage, and urban design parameters such as street width and building height. These correlations were found for energy performance metric that comprised energy demand and various solar potential indicators, such as total PV generation or solar radiation on building envelope. So not to be confused, I would like to briefly introduce some of the parameters that we're going to talk about a lot today. And these are site coverage, which is the ratio between building footprint area and site area. Then building footprint area, which is actually equivalent to the floor area, and so-called FAR, floor area ratio, which is a ratio between gross floor area of the building and site area. So let's move forward to the typological-based energy-driven urban design studies. So often these studies use typological method to represent and classify urban form. Three types of this method can be distinguished. The simplest one is generic building patterns with repetitive context. Simply generic forms are used, as you can see in this picture. Target building is the one performance of which is analyzed, and context serves as surroundings to this building. This method, however, struggles to represent the actual build form because it is overly simplified. Second method uses actual build form of studied urban area by, for example, exploring GIS data of a city, and this requires big computational effort. And finally, third method uses hybrid targets with repetitive contexts. Hybrid targets can be vernacular typologies that are present in the studied area, and the context can be simplified with generic typologies. So this method is a good compromise between two. In these studies, the design parameters that are used to describe urban form include floor area ratio, building or block dimensions, building footprint, street widths, and land use mix. Here are some examples of the way researchers apply typological method. On the left side, Singapore-based study of my colleague Zhong Ming is presented. He used generic patterns as a starting point. Then he verified them for Singaporean context and came up with various block typologies that are relevant for Singapore. For example, a block would comprise a combination of podium with a tower. And the aim of the study was to estimate PV potential of each block typology. And on the right side, the study is shown that is also based in tropical climate, but in China. These typologies were retrieved by studying urban form of the city of Macau. For example, these typologies include courtyard, pedestal, cross, and so on. And then the result of this study was to prove that one of the typologies, which is set back, maximizes solar accessibility, and also pedestal, court, and triangle perform quite well. These are the final studies that I would like to share with you. Some of the Singapore-based studies, not necessarily the ones that were using typological method, could actually quantify the relationship between studied urban design parameters and performance metric. And here we can see what I mean by quantifying a relationship. It is to make a clear statement how a change of a design parameter would influence performance metric. For example, to increase renewable energy share from 20 to 70%, FAR should decrease from 32 to 3 with purely residential land use. Another example is here. Hybrid and courtyard typologies have twice the rooftop PV potential, as well as twice higher reduction in CO2 emissions than other typologies used in this study and shown here. So these are the examples of a good outcome that one can expect to get out of energy-driven urban design studies in order to derive some heuristics. And hopefully we can hear something similar later in the results section. As now we have some background from the literature review, next I would like to talk about the methodology of the current study. First of all, to describe urban form, typological method was used. As block typologies lead to large amount of design combinations, it is difficult to interpret the results, and sophisticated parametric tools are needed to generate the designs. That's why this study chose building level as a typology unit to gain more control over the modeling interpretation of the results. The building typologies from Macau that were shown earlier in the literature review were used as a starting point. They were verified for Singaporean context by studying building footprints in high-density areas of the city. As you can see, these typologies were appeared to be present in Singapore, and 12 of them in total were adopted by this study, including square, courtyard, slab, C-shape, L-shape, and so on. So to describe these typologies, the most relevant parameters in context of energy-driven urban design were chosen. According to the literature review, this includes density, expressed as floor area ratio, street width as compactness indicator, and land use mix. The ranges for the parameters were defined based on Singaporean context, and mixed-use high-density setting was assumed. So for example, there is a minimum FAR of 4 and maximum FAR of 24, 3 typical street width categories for Singapore, and 36 different land use mixes, including residential, office, and retail use. Further, these land use mixes were grouped into 9 categories to simplify the interpretation of the results. And these categories include mostly residential mix, mostly residential with office, balanced use mix, and so on. So given these parameters, so-called scenario parameter matrix that you can see in this picture was constructed. This means that for every typology, each possible combination of design parameters was tested. For example, square was 60% of residential use, 30% of retail, and 10% of office. Then FAR of 4 and street width of 15. The total number of scenarios reached more than 9,000. The performance indicators for the scenarios included operational CO2 emissions, energy use, both absolute and relative values, and renewable energy share. As for the supply systems, given the goal of achieving low carbon performance, the set of technologies that was chosen was constant and was already known as well-performing typologies, so technologies. This includes district cooling and photovoltaic panels installed on the roofs and facade with a threshold of 400 kilowatt hours per square meter per year. And the rest of the demand is assumed to be supplied from grid electricity, assuming Singaporean mix. So let's look what scenario parameter matrix means for district geometries. Here you can see districts containing different building typologies. Total number of buildings in the districts was chosen to be 25, with 9 target buildings in dark gray and 16 surroundings in light gray color. Same number of buildings was assumed previously in several energy-driven urban design studies. The buildings are oriented in a way to reduce solar exposure of the facade facing east-west direction, which is a common practice in Singapore. Further, constant site coverage and site area were assumed. Site coverage was 45% and site area of 100 by 100 meters. If we keep street width constant, but increase FAR from 4 to 14 to 24, this means that given this constant site coverage and constant site area, the building height should become larger. So the building grows, but footprint area stays the same. It is also assumed that the height profile of a district is homogeneous in this case study. Next, if we keep FAR constant and we increase street width under constant site area, the building footprint has to get smaller. And therefore, to achieve same FAR with larger street widths, building height should also increase, which happens from left to right. If we speak about compactness of urban form, a district with larger street widths would be less compact than a district with smaller street widths. So street width in our case is an indicator of compactness. Also, I would like to mention that since larger street width means higher buildings, maximum achievable floor area ratio is different for street width of 45 compared to the category of street width 15, given a certain height limit. So if maximum achievable FAR for street width 15 for the buildings is 24, for street width 45, it is only 10. In the second case study, the assumption of homogeneous height profile of a district was challenged. The total number of 10 height profiles was investigated. To reduce computational effort, scenario parameter matrix was reduced to a single land use mix, 2 building typologies, square and slab, 2 densities, 4 and 10, and 2 street widths. The total number of scenarios reached 18. So the first 5 height profiles that you can see in this picture are inspired by the idea of transit-oriented development, which leads to a pyramid district shape with density concentrated at certain location. The apex of the pyramid with the highest FAR can be either located in the center or at the edge of the district. So in total, we have 5 designs with different orientations. Additionally, height profiles such as stairs and corona shape that have been used previously in the literature were explored. Stairs shape can be used in urban design to maximize use on one side of the district, for example, here if it faces the river or sea. And corona shape contains a smaller building at the center of the district surrounded by higher buildings, which can occur, for example, if building in the center has different use, such as a restaurant or school. And the surroundings in this case study were assumed to be of homogeneous heights for all district designs. In the final case study, assumption of constant site coverage was challenged. Except for 45% site coverage, additionally 70% and 90% site coverage were investigated. Also here, reduced number of scenarios was considered. A single typology of square was tested, 3 densities from 4 to 16, 2 street widths, and single land use, same as in the previous case study. So total number of scenarios reached 18. To obtain the results, the following workflow with various tools along the road was created. District typologies were generated in rhinoceros with help of grasshopper. Then they were enriched by coordinate system and QGIS. Energy simulations were conducted with help of city energy analyst. And finally, statistical analysis of data was done with stats model package in Python. As for the statistical analysis, to perform statistical analysis, first ANOVA technique was used, analysis of variance. It is a hypothesis test that helps to explore relationship between factor variables and performance indicators. In our case, for example, a factor variable is building typology that consists of various elements such as square, slab, and so on. So one way ANOVA helps to determine, for example, whether the average CO2 performance differs for at least one typology out of all considered elements. Then null hypothesis, meaning that means of elements are equal, is rejected if p-value is smaller than 0.05. Two-way ANOVA additionally studies interactions between two factor variables. For example, interaction of typology and FAR with respect to energy use intensity. Let's say for one typology, increase of FAR would mean lower energy use intensity, and for another typology, higher. Then the null hypothesis would be rejected by two-way ANOVA. Next statistical analysis technique was a linear regression. It was used to approximate and quantify the relationship between the input variables and performance indicators. A regression model of a linear form was used, where typology, FAR, and so on are independent variables. And the aim is to estimate the unknown coefficients in order to predict performance indicators based on the input variables. The estimated coefficients can be interpreted relative to a baseline scenario. In this way, for example, the regression coefficients can be used to estimate the effect of an increase in the proportion of retail area, let's say on the carbon performance of the district relative to the baseline. And now we're finally coming to the results section. To get a big overview, let's start with one-way ANOVA. I'm going to address each input variable, land use mix, typology, FAR, and street widths, considering various performance indicators. The results that I'm going to share will be filtered for maximum FAR of 10 to use equal number of observations for each street width category. Also, some of the typologies such as pedestal, cross pedestal, and setback will be excluded since they follow different logic in terms of maximum achievable density for each street category. So let's start with land use mix and energy use. The null hypothesis is rejected for both absolute and relative energy use, which means that there is substantial variability of the results for different land use mixes. In the figures, we can see that land use mix with retail component have the highest energy use, while the residential dominated uses have the lowest energy use, as expected. Balanced scenarios offer a good compromise between these extreme cases. If we consider Singaporean standard for super low energy building and take benchmark value, for example, for offices of 114 kilowatt hours per square meter per year, we can see that actually none of the scenarios with office use would satisfy this benchmark. Next, null hypothesis was also rejected for renewable energy share. We observed that land use mixes that would require highest energy demand have the lowest renewable energy share, for example, mostly retail. So the higher the energy demand is, the lower the renewable share is. And maximum renewable energy share is around 18% for mostly residential scenario, if we consider FAR of 4 and street width of 15. For CO2 performance indicators, null hypothesis was rejected too, and CO2 performance basically repeats trends of energy use that we have seen previously. Next, let's look at the typology. In the case of energy use intensity and CO2 intensity, null hypothesis was not rejected, meaning that there is no substantial variability between different typologies. The null hypothesis was also not rejected for absolute values of these indicators. However, judging by visual inspection, we can see slightly better performance of slab and square in energy use intensity, as well as triangle and courtyard in CO2 intensity. Only for renewable energy share and PV potential, null hypothesis was rejected, suggesting inequality of means for different typologies. The highest PV potential and renewable energy share was reached for courtyard, triangle, and square. On average, it was 9% of renewable energy share. This percentage is too low to create substantial PV-induced variability in other performance indicators. That's why we didn't see similar behavior of the CO2 performance. If we consider FAR, as expected, the null hypothesis was rejected for energy use and energy use intensity. We observe increase of energy use with FAR, since the gross floor area also increases, and light decrease of energy use intensity. Moreover, step change is larger for smaller FAR. If we look at the step change between 4 and 6 here, then for bigger FAR, if we look at the step change between 8 and 10, I suppose that the reason for it is increased mutual shading, because the ratio of shaded area is larger if buildings get higher with larger FAR. So this decreases solar exposure of the facades and therefore cooling demand. Further, null hypothesis was rejected for renewable energy share, but not for PV, despite visual differences. It is necessary to mention that PV dataset had few observations, only 22, so ANOVA may not perform well with regard to PV. So here we observe decrease of renewable energy share and PV potential with FAR. The rate of change in renewable energy share is again not constant across different FAR. So renewable energy share shows a larger decrease between 4 and 6 than between 8 and 10. Smaller PV potential for larger FAR also indicates that most likely the mutual shading is enhanced, so it decreases solar exposure of the facades and negatively affects PV potential on the facades, but reduces energy use. As for CO2 performance, null hypotheses are rejected for both relative and absolute values, suggesting inequality of means. Absolute values follow pattern of absolute energy use. Even though energy use intensity decreased for larger FARs we saw previously, this pattern seems to be reversed for CO2 intensity, most likely due to the lower PV potential for larger FAR. Finally, let's look at the street widths. The null hypothesis was rejected only for energy use intensity. Wider streets lead to higher energy use intensity and visually to higher CO2 intensity, since mutual shading reduces and there is more solar radiation in the facades. Absolute values of CO2 and energy demand do not show any variability, so they're not shown here. As for the renewable energy share and PV potential, null hypothesis was rejected, meaning that there is substantial variability of the results. PV potential and renewable energy share decrease for wider streets, with a bigger step change between street widths of 15 and 32. It seems to be counterintuitive that PV potential reduces for wider streets, and facade has higher solar exposure. So let's have a closer look at the PV potential on the roofs and the facades to address this matter. If we look at the breakdown of PV potential for cross typology, we can clearly see that the total production decreases if we compare street widths of 15 and 32. But the difference between 32 and 45 is quite small. That's why we saw a bigger step change in the previous slide between street widths of 15 and 32. Also, we notice that the roof potential is constant within a street category. Change in FAR only causes a change in facade production, which slightly decreases for bigger FAR. Roof potential is higher for smaller street widths, because footprint area and therefore roof area are larger. While roof potential decreases, facade potential grows for wider streets since mutual shading of the building reduces. If we compare the PV breakdown of cross and square typologies, we can notice some differences for large street widths. In case of cross, facade production actually decreases with FAR, but rises in case of square. So these kind of occurrences are not captured by one-way ANOVA. So to address them, two-way ANOVA that considers two factors simultaneously should be used. Here are the results of two-way ANOVA for PV potential versus typology grouped by street widths. Null hypothesis was rejected, suggesting that there is an interaction effect between street widths and typologies. All typologies except for slab and square follow similar pattern. Wider street widths means lower PV potential. But for slab and square, street widths of 45 has actually better performance as street widths of 32. Apparently, PV production on the facade for these typologies can outweigh decrease in roof production due to a smaller roof area. So two-way ANOVA was conducted for other cases as well, and majority of them either didn't reject the null hypothesis or trends that were showed in one-way ANOVA remain constant. So we will not address it further. Let's move forward. In the previous analysis, we have noticed that there exists a very little variability of the performance indicators unless we talk about the influence of the land use. The variabilities that were arising from the geometry-related parameters such as street widths or FAR would be mostly caused by the differences in the PV potential. So the question is, if we assume maximum existing PV cell efficiency of 45%, which is quite future-oriented and is almost 3 times higher than the current cell efficiency, how will it change the results? In the figure, we can see that, of course, we can observe the reduction of CO2 intensities for higher PV efficiency. However, if we take FAR of 4, one can see that future-oriented efficiency may lead up only to 25% reduction in CO2 intensity, which is pretty disappointing compared to the almost triple increase of the PV cell efficiency. So we conclude that total PV production is still too small compared to energy use. Moreover, we can see that the trends of various size of step changes are amplified for future efficiency. If earlier we noticed that the trade-off between FAR of 4 and 6 is larger than between 8 and 10, with future-oriented PV efficiency, this effect is amplified. So let's summarize the findings of the first results block. The variability of the performance indicators is mostly caused by land use mix. Among other parameters, FAR has greater influence. The effect of varying street widths or typologies can be neglected regarding CO2 performance. Despite small overall variability caused by different typologies, the interaction effects of typologies with other variables are worth considering. For example, street width of 32 has higher PV potential than street width of 45, but only for square and slab. Regarding PV potential, interesting effects were observed for different street width categories and FAR that are mostly explained by change in mutual shading of the buildings. Finally, PV potential and therefore renewable energy share are too small to project the variability of PV potential on the performance indicators. Even triple increase of PV cell efficiency would reduce CO2 intensity only by 25%. Now, I would like to share with you the outcome of the regression model, which is a table on the right that can be created for every performance indicator. In this case, it represents CO2 intensity given following baseline scenario: square typology, FIR of 4, street width 15, and balanced land use. We are mostly interested in these coefficients. Coefficient with low standard error values and PV values close to 0 can be thought of important and contributing to the explanatory power of the model, which is not the case for the typologies. The rest of the parameters have PV values of 0. So I will give you an example how this table can be read. If one wants to know how CO2 intensity would change if land use changes to office with residential and FAR is increased to 10, then it would be necessary to sum up coefficients with baseline. And this is the result that one would get. Looking at the coefficients closer, one can spot some trends that we have discussed previously. For example, that the trade-off between FAR of 4 and 6 is larger than trade-off between FAR 8 and 10. So both statistical approaches, ANOVA and regression, support each other's findings. Another example can be made with respect to absolute CO2 emissions. If the goal is to minimize CO2 emissions, then we should go for courtyard typology and mostly residential mix, resulting into 13,000 ton reduction of CO2. To make this value tangible, let's compare it with something that many of us have experienced, namely flight from Singapore to Zurich. So 13,000 ton of CO2 would be equivalent to 38 one-way flights with 200 passengers. This is what we would save by such design decision. Also, these regression tables can be used for benchmarking purposes. For example, if one wants to minimize energy use intensity and achieve some good points from the construction authorities, then given the baseline, one could look at the possible reduction of the value. And for example, in Singapore, Building and Construction Authority says that you need to have 135 kilowatt hours per square meter to be in the top 10% of mixed development, so mixed land use mix. To achieve that, we would need to introduce the office component compared to the baseline, and then the benchmark of 135 could be achieved. So let's summarize. Regression model allows to quantify the impact of parameter change on the performance indicator, and the trends analyzed with ANOVA are also present in regression model. The findings are supported by both models. Regression model can be used for benchmarking purposes to estimate performance of certain combination of design parameters and compare different options, which is heuristics. So the previous analysis was only for the first case study, exploring the scenario parameter matrix. But as you remember, there were also 2 case studies challenging the assumptions of the first case study. Case study 2 assumed heterogeneous height profile of a district instead of homogeneous. And here are the results. Null hypothesis was not rejected in all performance indicators except for PV, so there are no substantial differences between different height profiles. The energy use was also nearly identical in all cases. However, some designs lead to higher PV potential, such as stairs-oriented shape towards east and corona shape, which are these box plots. They have larger PV potential on the facade. That's why the total PV potential is higher. So we can spot small differences in CO2 intensity for these height profiles too. They perform slightly better based on the visual inspection. As for the final case study with varying site coverage, ANOVA didn't reject the null hypothesis despite visual differences that we can spot here. Perhaps it's due to a small number of observations, which is 18. So we noticed that the higher site coverage leads to reduction of CO2 intensity because PV potential increases. The reason for that is increase in roof area that is twice bigger for 90% site coverage than for 45% site coverage. However, we do not observe doubled PV PV production since increase in site coverage reduces PV potential on the facade. So roof potential increases, but facade potential decreases for larger site coverage. So challenging the underlying assumptions of case study 1 actually hasn't shown large impact on the performance indicators. However, there were significant differences in PV potential observed. But still, the renewable energy share is too low for PV potential to cause significant variation in other performance indicators, such as CO2 intensity. And now we have slowly arrived at the conclusion. First, let's address the conclusions related to the design parameters. The most impactful design parameter is land use mix. The impact of FAR is much smaller, but statistically significant. In some cases, the impact of street width is statistically significant too, while typologies do not cause significant variation. The lowest CO2 intensity of 33 kilograms CO2 per square meter can be achieved with mostly residential land use mix, street widths of 15, FAR of 4, and triangle typology. CO2 intensity is largely determined by energy use that is influenced by land use mix. The only source of the variability in the CO2 performance originates from differences in PV potential. PV potential varies with the FAR, site coverage, height profile, and street width, but shows less dependence on the choice of building typology. And renewable energy share is too low to observe PV-induced variability in other performance indicators such as CO2 intensity. To increase renewable energy share, the change on the bigger scale should happen, namely reduction of CO2 intensity of Singaporean electricity grid. So only multi-scale approach can lead to low carbon districts and buildings because the potential of urban form only to influence carbon performance is limited. So what are the achievements of this study? The framework developed by this study can serve as basis for future energy-driven urban design studies. One way ANOVA analysis provided a big picture of the prevailing trends in the data, and two-way ANOVA with higher level of detail revealed some unobvious relationships between different variables. Regression model provided heuristics and estimated performance indicators based on certain design combinations. This can facilitate decision-making process of early urban design stages. And finally, I would like to give you an outlook on how this study can be further refined. So more realistic urban settings should be considered by using parametric design techniques, and it should account for hybrid block typologies. The final case studies should be carried out according to the full scenario matrix in order to incorporate height profile and site coverage into regression model. Also, load match index can be used as more detailed performance metric for PV potential, not just the annual PV generated electricity. To improve accuracy of the energy simulations, calibration of energy use for different typologies should be carried out. And finally, the assumptions at the building level should be influenced by land use mix. For example, higher window to wall ratio for office dominated land use. Then the results of the study can be refined. With this, I would like to conclude. Thank you very much, and I'm looking forward to your questions.
All right, thank you very much, Anastasiya. That was a great intake of information regarding urban form and energy systems, optimization and performance. That was great. Thank you very much for that. Maybe I can start off with some questions regarding the results you obtain. So in slides 30 to 50, I believe, you started describing all the box plots, which basically represent probability distributions of the impact of one variable against another one, right?
Exactly.
And I wonder if you have some intuition about what we can see in the extremes of those plots, on the maybe on the third quartile and the first quartile, as well as the
Yes, this is
fourth
a
quartile, the
very
first one.
interesting question. Thank you. So we can start probably by looking at the renewable energy share compared with an FAR. So we know that for higher energy demand that is caused by the land use mixes with a high retail component, or also high office component compared to residential mixes, we get less renewable energy share. So here at this point, for example, 8% of renewable share for FAR of 4, for sure there will be a land use mix that has the highest retail component. Also, most likely, there will be the highest street width of 45, because we have seen that the street width of 15 actually performs better in terms of renewable energy share. And here on the top points, there will be always a land use mix that contains mostly residential component and the street width of 15. While it is difficult to make a statement with regard to the typologies, because themselves they show very little variability. And on average, the triangle has quite a high renewable energy share. So most likely it is also located in this top points. And basically following same logic, one can look at each plot, because the most important finding that we have is that the land use mixes with retail component have the highest energy use, which has actually been known from before. And that's why it is always difficult to achieve high renewable share with such land use mixes, and therefore achieve lower CO2 emissions. So if we look at the CO2 intensity, then of course here there will be same situation. At the top of this whiskers, there will be the land uses with high retail component, and at the bottom there will be those with low residential component. And also the interesting finding probably is that the order of these scenarios stays the same, more or less, for different parameters.
All right, thank you for that. Maybe just a follow-up quick question regarding that intuition you just brought to us. I mean, we are mainly engineers, at least you and me, and there is always the question on what would be your take, not necessarily as an engineer, but in the having the reasoning that you can perhaps influence how a future district or precinct can be designed in the future. It'll be great to hear from you. What is your take based on the data you observe on how to achieve a low carbon district? What would be the conclusion in terms of FARs, the street widths, etc., that you will say, hey, designer, take into account these three top things,
Yeah.
and that is your take on how it should be designed.
Yeah, sure. So we know that there are always trade-offs, so it's very difficult to say what is the best performing solution. But as I stated in the conclusion, the best performing scenario would be the one with mostly residential land use mix, street widths of 15, FAR of 4, and triangle typology. So the lower the FAR, the better, the lower the street width, the better. And we have already talked a lot about the land use mixes. But in general, if we move to a bigger picture regarding this study, I would say that I was slightly disappointed that the impact is less than expected of the urban design parameters that were considered in the scenario parameter matrix. So the achievement of low carbon performance only considering and optimizing these design parameters is not sufficient. That's why indeed multi-scale approach is needed, because largely the buildings are supplied by the electricity from the grid. And let's say if the Singaporean grid will be more similar to Swiss grid that has a very high renewable energy share, then the differences of these urban design parameters that I have shown in this study, they will become more significant and they will become more visible. And then actually they can become also a higher priority to consider them in the design. And now if we speak about the priorities, of course, the change should happen simultaneously on different scales. But if we just speak about low carbon performance, actually the biggest impact would be to change the way power system is designed, if we speak about Singapore, and change the electricity mix. And then it would be much easier to achieve low carbon performance of the designs.
Okay, maybe just a clarification from one comment you just made. I think you wanted to say the opposite. If you have a carbon mix lower than Singapore, that would be the Swiss one, for example, would be at least half. Then actually you could do the impact of PV, etc., would be lower.
Yeah,
because yeah, right. That's what you wanted to say. Just to clarify.
Yes. I wanted to say that, and the impact of PV actually is very small in the current study, but I imagine that if we assume that the renewable energy share of the electricity grid is 100%, right? If we assume that this is just the clean CO2 neutral electricity grid, then actually there is no point exactly of playing around with PV.
Mm-hmm. All right, thank you.
Maybe I can follow up on that. Thank you very much, Anastasiya. That was very comprehensive. I'm very excited which jump you took after your midterm to this. I mean, this is really, you really switched gears. A very good introduction and motivation, very well explained. I like the setup of your studies, which I think are very comprehensive within the target you were aiming for. I like very much how you choose your methods and how you analyze this. I think there's on different levels very interesting insights. For example, on the behavior. Obviously, some trends were to be expected, but for example, that some trends are not linear, and that there's this interesting steps in between. For example, for FAR, I think that's a very interesting insight. Also, obviously, this coupling of parameters as you introduced, that's very interesting. I haven't seen that before, and I think that leads to very interesting insights and moves us away from just looking at single parameters. And the second part where you show this very nicely is this mix, that if you look just as a single parameter such as PV production, then the changes are very much pronounced. But if you look at the total EUI, or if you look at the mix of different parameters, that then gets kind of obfuscated or mixed in a sense, so it doesn't actually matter that much anymore. So I think that on a big level, there's very interesting insights. A lot of my comments you already had in the outlook. I like your stab, or you look into the projection of future technologies and technology development. So I think you did a very good job of doing your study, and it has very interesting insights. Obviously, what you just mentioned holds true. If everything would be decarbonized, we don't have to think about anything anymore. So that's very true.
Yep.
But what is interesting, and in Swiss context, you would have a grid with much less CO2 intensity. But on the other hand, you would have very different boundary conditions, right? You would switch from a cooling case to a heating case. And certainly one extremely interesting thing would be just to plant your study in a kind of a European heating dominated context and see how this would change. I mean, that would be almost like a dream come true in a sense, just flipping the context that you have and then seeing what would happen then afterwards. And
Well, actually, I tried to plan the study in a different location, but still within the tropics, to see how the results would change and if we can generalize the conclusions speaking about the tropics and not only Singapore. And here, actually, there was something interesting that came up. If we compare Singapore and Bangkok, obviously the sun angle is different, and then it's completely different story about the trends in PV production, because if in Singapore we saw that square and slab, they do perform differently than other typologies, but mostly if we compare FARs, the larger the FAR is, the less PV production we have. But in Bangkok, this would be completely the opposite.
Mhm.
So I think that the sensitivity analysis regarding the different location, it is a very important point, because this changes the perspective a lot. However, then when we consider other performance indicators as CO2 intensity, renewable energy share, again,
Right.
these differences are not that visible anymore.
Exactly. I mean, and that would be, I mean, for multiple reasons, that would be extremely interesting. And like, ideally, you would like extrapolate the study and putting this on 10 different locations on the globe, and then seeing, okay, what can you learn from this? And then you would actually have kind of global index on responses to low carbon cities. I mean, the methodology you established, I think, is super comprehensive to do these type of studies. And as you mentioned, in the Swiss context, you would have, yes, a lower CO2, but you would have much steeper sun angles. So the seasonal distribution of solar radiation would also become much more dominant, right? So especially with respect of the form factor of your buildings and the generation potential on the facades versus the roof. It's very clear that in Singapore, this is very much dominated by the roof. But if you switch that
Exactly,
to
yes.
Zurich, then of course the facade exposure, especially on spring and fall, is something where you can show that you actually generate much more electricity than on the rooftop, just because you have this area available. And then of course, how much it is shaded, how much is exposed to the sun would become extremely relevant. So we should, in any case, try to, I don't know how much effort that is, but obviously it would be fantastic to have this methodology on different contexts and learn from it. Because I believe, nevertheless, the results, it would be interesting. First hypothesis, this levels out again, right? You showed very nicely that different parameters kind of equal out if you look at the big picture. So the hypothesis could be, yes, in our context, it would also level out because lower CO2 intensity of the grid, but different boundary conditions for heating and solar radiation. But then it's interesting that you might also have situations and locations where this doesn't level out, it just multiplies in a sense, right? Because you have different boundary conditions on a larger scale. But that would be extremely interesting. One thing I was wondering, sorry.
Yeah, I just wanted to say that probably one advantage of this framework is that you can combine it with different modules and different angles and perspectives and use it for different locations and change the urban design parameters in the scenario parameter matrix. So actually there is lots of work that can be done further.
Yes. So I was wondering, and that's this guy, I mean, obviously to do that, you have to take a lot of simplifications also on the modeling side. I was wondering, I mean, certainly there are parameters that you're not considering. For example, window to wall ratios, I mean, you keep this constant. Position of windows, that then makes a big difference depending on the urban context. Then certainly irradiation thresholds, all these things you maintain more or less the same. So I was wondering, from this, the parameters that you kept at the same level for the entire study, which one, just from a feeling, do you think, is there a parameter where you would need a higher resolution to, and that would change the picture somehow?
Yeah, I think that definitely it is a window to wall ratio, because it was kept 40% for all the case studies to allow for PV panels on the facades. However, we have seen some results regarding the energy use that were a bit unexpected, let's say. That the change actually for different FAR is quite small, and in general the change of energy use was very small if we also compare same typologies. So this raises the question how far this window to wall ratio of 40 depicts the situation of different solar irradiation on the facades. Because if we could see it clearly for the PV panels, we couldn't really notice this effect with regard to, let's say, increasing cooling demand if the solar exposure of the facade increases. I could make some assumptions in some cases that yes, this is the reason, but the magnitude of this effect was very low. So I suppose that if we increase window to wall ratio, for example, for office users, for sure it can be increased, then we will see even more trade-offs between higher cooling energy demand of the building if the solar exposure of the facade increases, and then higher PV production, and how it balances each other out. So this interplay would be very interesting.
Well, also, I mean, that could be something that could be coupled in a sense, because a residential typology has a different window to wall ratio than an office or retail typology if you look around in Singapore. So obviously, if you would couple that, well, maybe not that much in Singapore, and maybe maybe that's not true. Maybe that would be worthwhile looking, but just from a gut feeling, I would say that office buildings tend to have higher window to wall ratios than residential buildings. Of course, if you would couple these, then your effects, of course, would be pronounced and would probably would be a little stronger in this sense. And also, I mean, this would become more prominent in a cooling and a heating dominated context, because obviously the thermal losses to the windows are still 3 to 5 times as high than to the rest of the envelope. So this effect would even be more pronounced in a heating context, I would say.
Yeah.
Yes.
I think just to connect to that, I believe what very surprised me about these results and the sensitivity to other parameters that were not part of the main analysis was the idea of the PV efficiency, right? I mean, how disappointing is that we.
Can you explain that a little closer? That was a little quick. Can you explain the effect a little closer?
Which is very very interesting. Yes, please, Anastasia. Can repeat
Yes,
it.
yes. So we assume that the PV efficiency is almost 3 times bigger. And yeah, we wanted to see what is the impact on the results. And if we take now a comparison between FAR of 4, so this green box plot, and we take, let's say, median of it, and we compare the CO2 intensity, then there is only the reduction of 25% in CO2 intensity, given that we increase the PV cell efficiencies 3 times. So this suggests that still the energy demand is actually too high and the PV potential is too low compared to it to have some larger effect. And yeah, the trends and the differences between these different box plots, they are amplified, which is also interesting that we can kind of zoom into it. But otherwise, again, we can't do much playing around with PV.
Yeah, and it's looking at 44% of efficiency, right? Like basically what we, the maximum achieved ever in laboratory experiments, and very far of being in the market, I believe. We're talking about maybe 10 to 15 years to be in the market, that efficiency.
Exactly.
It's very,
yeah.
I mean, for me, it was very, I mean, when we planned the experiment, I didn't expect that was so little. Well, reinforcing the idea at the end, that is before you want to perhaps look into PV with high efficiencies, you have to rethink at least the consumption, right? At least for Singapore.
Yeah, true.
See, that's, yeah, I mean, again, this is this nice effect of a couple of parameters.
Back to base 0, right?
What?
It's back to base 1, sorry, back to base 1.
It's back to square 1, but also it also rejects a very common hypothesis that it's said, okay, you don't have to care about energy efficiency, it's all about generation, right? So that, I think that's an interesting point.
Yes, absolutely. At least in this context.
Yeah, so actually this study didn't really look at the building scale and didn't try to reduce the demand of the buildings. But yeah, ideally this should happen.
So again, it shows that there's unfortunately no silver bullet, right? It needs to be a combined set of measures to approach that.
Yeah, exactly.
Despite many people saying that this is the solution that will save the world, it's probably not just a single solution.
Correct. Just to clarify, how efficient are the buildings there in comparison to the average in Singapore? Just
so if we take this Let me find the benchmark, right? The super low energy building standard that you sent me once.
Yeah.
They say that the office building should have 114 kilowatt hours per square meter, ideally. Today, these values, I think, are around 170 on average, if I'm not mistaken. So actually with 170 still, that would be pretty efficient for office use, the buildings here in the analysis, but to achieve higher standards, they're not good for that.
But your base assumptions on constructive property. I mean, this also you didn't change, right? Constructive properties.
Yeah, exactly.
Average,
it is kept
average
constant.
lighting loads, cooling loads.
Yeah,
Can
yeah,
you show
yeah.
the detail there?
Yeah, we can have a look. So basically, most of the parameters were the default parameters of city energy analysis that were proposed for Singaporean context, and then some of them were verified to fit in my study, such as window to wall ratio, but the rest was not really changed. So we have the tightness level, which is tight, which is already pretty good in the city energy analyst. Then for external wall construction, we assume a concrete block, concrete floors also. As for the glazing, it is double glazing without shading. I didn't take shadings into account. And then
There's no shading, so
no
it's all
shading.
cool.
Yeah.
Okay. Wow.
Yeah. So it's double glazed only without emissivity coating. Yes, and kind of a balanced construction type, which is a medium construction. So I didn't try specifically to achieve with this parameter a super good performing building. That wasn't my goal.
Yeah. No, I think that's a very realistic setting, but again, it opens up what would be the most powerful retrofit in a sense if you take this as a standard, right? What would be the most powerful? I mean, not taking shading into account certainly, I think, is a big aspect in Singapore. So especially if you have this all year round, so I would assume you have a big drop in cooling. Do you have anywhere like a comparison of loads of your standard building?
No, I haven't looked at the loads, but I can probably do it for the report.
That would be interesting, just to see, okay, is the distribution of loads somewhere in the ballpark what you would expect? Then obviously you could already indicate. I mean, there's some retrofits that would be super easy, like exchanging lighting systems for like demand controlled lighting and LEDs and all these kind of things. So it would bring you down certain watts per square meter, but probably most powerful would be the shading. Right?
Yeah, the shading. Yeah, the reason I didn't include the shading because I wanted to look at these effects of different solar exposure of the facades if the streets are wider or buildings are higher. So that was the motivation behind.
It's not a criticism on your approach. It's just the question if you look at that from the different end of reducing that. I think that's a perfect setting, starting with an assumption of a very medium quality construction, and then also asking, okay, what type of retrofits would allow us to move stronger in this direction, given that this is not a singular solution.
Yes, this is definitely a step forward.
Yeah, very interesting. So how can we transfer this to our context? How much, what would you estimate? How much does it take another master thesis to do this for Switzerland, or is this an effort of, I don't know, a month or something?
This is an interesting question. I think that definitely it's not another master thesis because the framework is already there. So the only thing that needs to be changed are the geometry files. They have to be fitted for and the construction properties, and then the simulation they have to run for another 3 weeks. Yeah. But since the framework is here and the general ideas are here, it is always easier to start with the basis that already exists.
So we should definitely find a way of replicating that for a Swiss context.
Yeah, that
or
would be
European Union context. given a difference in situation, for example, with electricity mix, but that's something that can easily, probably the easiest parameter to change is the amount of the CO2 intensity of the electricity grid.
Yeah, yeah, that would be interesting.
All right.
So,
sorry.
yeah,
Sorry.
I'm very much looking forward to your report and going through in detail your very high amount of different results. Again, congratulations. I think it's a fantastic work. I'm very excited. Very
Thank you.
comprehensive. And thanks for enduring this difficult situation in Singapore. given the boundary conditions you had, I think it's even more. I can congratulate you.
Thank you very much.
Yes, the same from my side, Anastasiya. Great work. It's been a pleasure working also together on this topic.
Yeah, same.
Especially because you know it's also a step further to the research we did at Muses in the last 4 years. So actually, I think you made a really good job of putting everything together and enhancing it. And as Arno said, there are multiple possibilities to continue this research. So that's fantastic. I think we are over the time already, but we have an audience also, about 20 participants who join us today. And I'd like to give the opportunity maybe for 1 or 2 quick questions to Anastasiya, if somebody has it at this point. You can just make a reaction or just talk.
Hello, Jimeno.
Hey, Alberto.
Yeah, so I have one question, if I can, very quick, because I know you are already over time. But well, first of all, I think it was a really interesting presentation, and I really like the approach and the discussion on the results. The question I have is related to one of the points for the future work. If I understand correctly, one idea is to check when you combine a hybrid scenario with different topologies, right? Now, it also seems from your discussion that simulation will take a lot of time to run, right? So I guess that doing what you have done here may be a little challenging in that case, because you will have many combinations, many scenarios, many simulations.
Exactly.
Right?
Yes, exactly. This is a very good point. And unfortunately, that's why it was not possible in this study also to diversify the urban setting, and they were quite simplified. But for example, what Sean Mink is doing in his PhD, he's using so-called urban block generator that allows you to randomize these hybrid blocks based on some elements that are verified for Singaporean context. And then he couples this with the energy simulation, which still takes time, but it is a more automated process, because there exists a city energy analyst element directly in Grasshopper. So probably you can avoid this multiple transition between different softwares. That's why if we use such tool, this actually can become slightly easier.
Yes. The reason why I'm mentioning that is because in the past I was working on similar problems, and then we developed this. It's a black box optimization tool, where basically you have all your parameters as input, and then you link that to the simulator. And let's say you want to minimize the CO2 emission, and this tool will allow you to find the solution in terms of mix, for example, of different types of buildings that give you hopefully a good value of CO2 without the need to try all the possible combinations. So it's especially designed for problems where simulation will take a lot of time and you don't have enough, let's say, computational power to run all the simulations. So it's something that hopefully after a few simulations is already giving you a good result without the need to try everything. So maybe I can share with you later by email something more about that, because it may be something that can help you in that direction.
Yeah, thank you very much.
Maybe a comment to that. Obviously, optimization would be a solution to reduce that and to run that automatically. But I mean, it's explicit that this is not an optimization, but a step process, because in optimization at the end you get one or a couple of well-performing solutions, but you actually don't learn that much on the way, right? So what is nice about the approach that Anastasiya did, which I very much like, and I mean, there was also in Muse's optimization approaches tested out. What I very much like is that exactly going through this in a rather painful process allows you to identify these type of tendencies in between. So I think that's very worthwhile, especially with the aim, and I think that needs to be stressed in your work, is to inform people that make these type of decisions in kind of a heuristic way, right? Understanding the interdependencies and being able then to take the decisions.
Yeah, it is more transparent in general, this kind of approach.
Yes, I mean, I agree that having a black box is something scary because you don't know what is inside the black box, right? At the same time, I think if you can, using that approach as a kind of pre-processing in a way, so you identify good combination, and then with that subset, you apply your methodology, maybe it could be something that is interesting. I'm not saying just, yeah.
You could end up with a, a collection or grouping or clusters of different solution groups, so to say, and that would also allow you to see some positive trends.
Yeah,
definitely. Yeah.
Okay, thank you.
Yeah, thank you, Alberto.
Great. One more question, perhaps, from the audience? Pressing question? If that's not the case, then yeah, or is somebody talking? I don't see. No? All right.